In the previous video, we learned that a qubit is described by two amplitudes alpha and beta. And we are also learned that probabilities are obtained by squaring the magnitude of those amplitudes. P of 0 is modulus alpha square, P of 1 is modulus beta square. But here is the important question. If a qubit contains both possibility at the same time, how do we actually get a single result? That process is called measurement. Measurement is the process where you get a single result. Okay, like the thing is, if a qubit contains both possibility at the same time, but you have to get the single result. Okay, and that process is called measurement. Measurement is the moment when the quantum system produces a classical result. Measurement is the moment when quantum system produce a classical result. Okay, measurement is the moment when quantum system produce a classical result. So before measurement, the state is get C equals alpha beta. After measurement, the state becomes either get 0 or get 1. The probability of these outcomes are determined by amplitude alpha and amplitude beta. Okay, so probability of getting 0 is modulus alpha square, and probability of getting 1 is modulus beta square. And we already know that modulus alpha square plus modulus beta square equals 1. So the probability add up correctly. So let me explain this with a simple numerical example. Suppose our state get C is 0.6 and 0.8. Let's compute the probabilities. 0.6 square equals 0.36. 0.8 square is 64. Okay, 0.64. This means if we measure the qubit many times, 36% of the time result is 0, and 64% of the time result is 1. Measurement is probabilistic. It does not always give the same result. But if you repeat the experiment many times, the frequency approach the probabilities. Okay? So before measurement, the system stores both possibilities. Let me write it here. But if you have any more questions, don't worry. I will answer all the possible questions that you might have. Okay? So watch the full video. So before measurement, the system stores both possibilities. Okay, but after measurement, the system becomes the observed state. Okay, after measurement, the system becomes the observed state. Become the observed state. For example, if measurement result is 0, if measurement result is 0, the new state becomes get 0 means 1 0. If measurement result is 1, the new state becomes get 1, which is 0 1. This change is called collapse of the quantum state. Let's write it over here. This change is called collapse of the quantum state. Okay, quantum computer performs calculation using amplitudes. Okay, quantum, as you all know, I have already said this many times in my videos, quantum computers perform calculations using amplitudes. Okay, quantum computers perform calculation using amplitudes. Okay, but when we read the result, we must measure the system. When let me repeat it again. But when we read the result, we must measure the system, and measurement converts quantum information. The measurement converts quantum information into classical information. Okay, so measurement converts quantum information into classical information. This connects quantum into classical world. Okay, I hope you get it. So the final summary here is a qubit stores amplitude alpha and beta. The probabilities of outcomes are, let me write everything here so you can get this. A qubit store amplitudes alpha and beta. This is the first point. Second, the probabilities of outcomes are the probability of outcomes are modulus alpha square and modulus beta square. Okay, when we measure the system, it randomly produces one outcome according to those probabilities. Okay, so the third point is when we measure the system, it randomly produce one outcome according to those probabilities. Okay. So a qubit stores amplitudes alpha beta. The probability of outcomes are modulus alpha square and modulus beta square. When we measure the system, it randomly produces one outcome according to those probabilities. Okay, and after measurement, the state collapses to observed result. Fourth point is, and after measurement, okay, after measurement, the state collapse to the observed result. Okay, so if we draw this visually, quantum state, then our amplitudes alpha beta, then squared magnitude, then probabilities, then measurement, okay, measurement, then result, 0 or 1. So now let's discuss the most important thing in our quantum from zero series, which is confusion about the equations. Okay, so there are many equations. Cat C equals alpha cat 0 plus beta cat 1. Okay, these equations, like how does everything connects. Okay, let me explain everything here. So the first equation is state of the qubit. But if you already know this, you can just skip this part. Cat C equals alpha cat 0 plus beta cat 1. This equation means the qubit has two amplitudes, alpha for state 0 and beta for state 1. Okay, this equation means that qubit has two amplitudes, alpha for state 0, beta for state 1. Okay, now the vector form, and now let me write it here. This is the first one. The second one, the vector form. Okay, vector form of the same state. This is the vector form of the same state. This is the exact same state written as a vector. Both equations represent the same qubit. Both of these equations represent the same qubit. Now let me show you the probabilities. The probabilities P of 0 is modulus alpha square, P of 1 is modulus beta square. When we measure the qubit, these amplitudes determine the probabilities. Okay, when you measure the qubit, these amplitudes determine the probabilities. Now the measurement was, like, the measurement result is either cat 0 or either cat 1. Okay, after measurement, the system collapses to observed state, and these are the observed state. If result is 0, cat 0 equals 1 and 0, and if the result is 1, then cat 1 is 0 and 1. The qubits start as a superposition, cat C alpha cat 0 plus beta cat 1. The amplitudes alpha and beta determine probabilities with modulus alpha square and modulus beta square. When you measure the system, it randomly collapses to either cat 0 or cat 1. Okay, that's it. Everything is connected. So now, important question for you guys. There's an important question. If the qubit is cat C equals 0.3, 0.954, what is the probability of measuring 1? You can pause the video and try to do it manually. Okay, so now let me answer it. To get to the probability of measuring 1, to get the probability of measuring 1, we square the amplitude of cat1 component. To get to the probability of measuring 1, we square the amplitude of cat1 component. Okay, so 0.954 square. This is how we get the probability of cat1. So this will be almost 0.910. Okay, almost equals to 0.910. So we can write it here, p of 1 equals 0.91, almost equals to 0.91. That means probability of measuring 1, the question is here, let me write it over here so you can better see it. So from this we can say that probability of measuring 1 is 91%, and probability of measuring 0 is almost 9%, because probability must add to 1. Okay, because probability must add to 1. Okay, let's discuss what this means physically. If you prepare this qubit many times and measure it about 91 times out of 100, result will be 1. Okay, result will be 1. And about 9 times out of 100, result will be 0. But each single measurement still gives only one result. Okay, each single measurement still gives only one result. That's the key idea of quantum measurement. Okay, that's the key idea of quantum measurement. That's the key idea of quantum measurement. So one small detail over here is get C equals 0.3 and 0.954 is almost normalized. Okay, it's almost normalized. Let's check it if it's normalized or not. How to check if it's normalized? Let's check it. 0.3 square plus 0.954 square. 0.3 square plus 0.954 square. If we square it and then add it, okay, it will be 1. So it actually perfect normalize. Okay, it's actually perfectly normalized because it adds to 1. You know why this adds up to 1? Let me tell you again. Quantum states must obey one very strict rule, which is modulus alpha square plus modulus beta square equals 1. This is called normalization. This is called normalization. Okay, this is called normalization. Before we move forward, let's summarize what you learned today. A qubit is described by amplitudes alpha and beta. So quantum states, amplitude, probability, measurement. A qubit is described by amplitudes alpha and beta. Okay, these amplitudes are not probabilities directly. To get probabilities, we square their magnitude. P of 0 is modulus alpha square and P of 1 is modulus beta square. To get probabilities, we square their magnitude. Okay, when you measure the qubit, we don't see the amplitudes anymore. Okay, when you measure the qubit, we don't see the amplitude anymore. We only see one classical result, 0 or 1. Let me write it over here. When we measure the qubit, we don't see amplitudes anymore. We only see one classical result. Which is either 0 or 1. Okay, measurement converts, this measurement converts quantum information into classical information. The measurement converts quantum information into classical information. Now let me tell you a powerful insight, a deep insight. Quantum computers do their computation before measurement. Okay, quantum computers do their computation before measurement. So quantum computer do their computation before measurement. During computation, amplitudes evolve. During measurement, information becomes classical. So quantum computation is manipulating amplitudes. Okay, quantum computation is all about manipulating amplitudes, and measurement is all about reading probabilities. Okay, this is why quantum algorithms focus on changing amplitudes, not probabilities. Okay, this is the core idea of quantum computing. Many quantum algorithms works by increasing the amplitude of correct answer. Many quantum algorithms work by increasing the amplitude of correct answer and decreasing the amplitude of wrong answer. So before algorithm correct answer amplitude is small and wrong answer's amplitude is large. But after algorithm, the correct answer amplitude is large and wrong answer's amplitude will be small. Then measurement reveals the correct answer with high probability. Okay, did you get it? The measurement reveals the correct answer with high probability. This technique is called amplitude amplification. Amplitude amplification. This technique is called amplitude amplification. This is the principle behind Grover's algorithm, quantum search, many quantum ML methods, many quantum ML methods. Okay. A quantum computer never directly stores the answer. It only changes amplitudes so that measurement is more likely to reveal the correct answer. But for all of these to work, quantum state must obey one very strict rule. Okay, I have written it here. For all of this to work, quantum state must obey one very strict rule. Alpha square modulus alpha square plus modulus beta square equals 1. This rule is called normalization. I have already said this. This rule is called normalization, and understanding normalization is the next step in our journey. Okay, so next video will be on normalization. Thanks for watching the video. I hope you understood the concept. Thank you.